Today will be probably maybe the last lecture on this Rademacher type of analysis. I want to, in very simple terms, describe an approach which has been very influential in statistical learning, which is large margin classifiers. So the idea is that you want to, when you do classification, you want to try to go after a separating hyperplane or separating function that increases the margin. Okay, it kind of makes sense intuitively that if you've got two phenomena that you're trying to separate, then probably the best behaving separator should be one that in some way maximally separates these classes. So we'll get there in the second half of this lecture, but first let me just remind you and finish a few things from last lecture that we didn't get time to do. By the way, homework 3 will be out tonight or tomorrow morning, so we're on time. So last time what we've discussed, actually over the last 2 lectures, what we've discussed is kind of this very natural progression where you start with what you want. You really want to show or understand why it would be okay to minimize empirical risk over a class of functions relative to some class of models. We first upper bounded by this gap in the so-called generalization error gap of the empirical minimizer. This could be a loose step, so that's already something to keep in mind. Then we went to the maximum over functions because f hat is a random function. We don't know where it is. So we just took the worst case maximum over a class. This could be a very loose step. And then we last class we upper bounded these uniform deviations by some measure of complexity of f. And in fact, this step is not loose. This step is within a factor of 2 upper and lower bound. So at least in the last lecture we haven't introduced really more kind of looseness. Okay. So the whole point now is that if we can show that this is small, then it must be that this is small. And in particular, if we understand how this behaves with n, say 1 over square root of n, that gives us assurance that if we take 1 over epsilon squared, order of 1 over epsilon squared samples, then we'll get an epsilon accurate classifier out of the sample. Right? Questions about this general approach? Very linear. We're just going upper bounds. Okay. All right. So we ended up with Rademacher averages of the loss class. So the loss class is the loss composed with f. That's a class that maps xy pairs into a value. We call the G, and the xy pairs, the data set we abbreviated as Z1 through Zn. Okay, this is just a reminder. So I want to look now at one more example. The examples that we've done so far have been, I tell you what this G class is, or the set G projected onto the data is, right? So I just gave you this non-script G, its shape or description, and we computed a bunch of different Rademacher averages. Now I want to give you instead is the script G, okay? So think of script G as, let's say, neural networks. What is the geometry of this set? So that's less clear, right? So let's start with an example where you can kind of try to get a hold of the geometry. I'm going to start with a class G, which is a class of functions Z maps to indicator that Z is, let's say, less than or equal to theta. And theta is a real number, and Z is a real number. Okay? So this doesn't necessarily immediately maps to a loss class of something, but let's just start with this. What do these functions look like? Here's the real line. Here's the theta. You pick theta, and this is just an indicator that z is less than theta. So they look like this. Right? That's the way these functions look. These are just step functions. And the step is at theta. Okay? Also called thresholds, if you wish. All right, so suppose I would like to understand this side. So I would like to understand the expected max over theta in R of expected indicator that now a random variable z is less than theta. Right? This is my g of z in my notation before. Now my g is indexed by theta. Every theta specifies a g. Minus 1 over n, sum of indicator that zi is less than theta. Okay. Now, expected indicator is just a probability, right? Expected indicator is a probability of this event. So what is the probability that z is less than theta? Do you recognize this? Probability that z is less than theta. First class in probability. CDF. That's a CDF. How about this one? It's an empirical version of a CDF. Right? So now the question is, can we relate the CDF to its empirical CDF for all theta at the same time? So if I fix one single theta, of course this is by law of large numbers or central limit theorem, this behaves as 1 over square root of n. So the main question is, what if I ask you uniformly, is it the case that for all theta at the same time, these two functions, one is random, one is non-random, empirical CDF and the true CDF, are they close? Right? And this is a question that was asked by Kolmogorov back in the 60s, 70s, or maybe even earlier. Okay. And so, in fact, Kolmogorov proved that the behavior of this object is indeed 1 over square root of n, same as if you had one function theta, if you had just one theta. So somehow you do not pay for having this uniformity for all, asking for all theta at the same time. Okay. Right. Well, we're adults. We're not children, so we should be able to prove what Kolmogorov proved, right? In the next 5 minutes. Well, if you look at this object, you can start thinking, okay, so how can I prove this? Well, you start thinking, okay, so maybe I can consider a finite number of theta, spread them out on the real line, prove it for each theta separately, and then try to put it together somehow, and that's not going to work. So this is not actually an easy problem. Okay? Now, you know this relationship, the symmetrization lemma. So the symmetrization lemma says that this is upper bound by 2 times expected over z1 through zn, right? So this expectation is over z1 through zn. And then expectation over epsilon 1 through epsilon n, max over theta in the reals of, okay, so we had 1 over n. I usually kept it outside of the expectation, but that doesn't matter. In a product between the vector of epsilons and the vector of evaluations of each indicator on the data, right? So let me just write it out as a sum instead of the inner product. Sum of epsilon I from 1 to n, indicator that zi's are less than theta. And now here comes the amazing realization. Fix z1 through zn. Think of them as fixed. This is the symmetrization, right? This is the inner product between a vector of epsilons and the vector of evaluations of this G on the data Z1 through Zn. Yeah, I wrote out this side. I mean, there is no loss function, but by doing the sum, right? So here again, my class here, G. I can each function of this form. I can write it. I can name it G sub theta, right? So now the class G projected onto Z1 through Zn is, let me remind you, it's the class of G sub theta of Z1, G sub theta of Zn as theta varies, right? That's the only thing that varies, right? If you want to go over all functions in G, you might as well just go over all functions and over all parameters theta, right? That's an indicator, and so forth. So this whole thing is just the projection is a subset of what? Each G theta takes on which values? 0 or 1. So these vectors are vectors of zeros and ones. And they are a subset of 0, 1 to the n. Right? So how big is this subset? Right? We need to talk about the size of this subset. That's another way to write the same thing. Right? So how big is this subset? Do we have, let me draw the cube. 0. Last lecture we considered a cube minus 1 to 1. This one is 0 to 1, doesn't matter. So this is all zeros. This is a point 1, 1. So what does this set look like on this picture? Do we have 0, 0, 0, 0 in the set? Can you realize all zeros using indicators? So how would you do it? You take theta to be minus infinity, right? So send it past all the data. The data are fixed now. That's the kind of the key. The data Z1 through Zn are fixed. Take any theta to the left of Z1. So you've got this point. How about the point 1, 0, 0, 0? Can you get that point? Let's say it's this point. Is that point available? Between the first and the second, exactly. Okay. What else is available? So the only things that you can get in that set are all zeros, 1, 0, 0, 1, 1, and then all the way to 1, 1, 1, right? Can you get anything else? No, that's it, right? How many other? N plus 1. And So the cardinality, let's write it like this, cardinality of this G projected onto Z1 through Zn is equal to n plus 1. Right? If the points are not overlapping, then it's exactly n plus 1. If they're overlapping, it's even less. Right? If x1 is equal to x2. Yeah, z1 is equal to z2. But I mentioned last time that the Rademacher averages of any set G of finite cardinality are bounded by some C log cardinality. Okay, I'm using different notation, sorry. Cardinality of the set G over n. Yep? So this is upper bounded by 2 times some constant square root of log n plus 1 over n. Does it go down to 0 with n? Yes. Did we get Kolmogorov's result? Not quite, but close. Right. Was that easy? Yes.
That's for a fixed set of z's.
Yes, so we proved it for a fixed. It's independent of the z's, so this doesn't matter.
So what did we just prove?
We just proved that empirical CDF and the true CDF are uniformly close over all the thetas as functions.
So we proved that the line above the generalization error.
Not yet. Let's just look at like this board. I'll come back to this in a second. Here there is no loss function. I'll introduce it in just a second. There is no loss function, right?
That's your loss function.
I just for a second think of this as just the definition of a class and nothing else. Good? You feel proud of yourselves? Oh, come on. Kolmogorov is like the greatest mathematician. Of course, we didn't quite prove the result that he proved, but you know, it's good enough to feel good about ourselves. So what made this simple argument possible? What made it possible is that we're able to condition on the data and work conditionally on the data, right? So even before, even though before this could have been, you know, infinite dimensional objects, these functions, once you condition on the data, you always have a finite dimensional object, an n-dimensional object. And so understanding the geometry of that object can give you a result conditionally on the data. And then...
But it seems all you need to do is find the cardinality.
But cardinality is not always the right notion. For instance,
Always give you the square root n.
it will not always give you square root of n because sometimes the log is too big. Yeah.
It could be exponential.
It could be exponential. It could be right. All right. So, what is Vapnik-Chervenenkis theory? This famous theory, foundation of machine learning. Well, I'm not going to go into the details, but let me just say that it's just about how big that subset of the cube is. So there is something called the VC dimension, Vapnik-Chervenenkis dimension, of F, or of G, let's say, of a class G. And if it is infinite, if VC of G is infinite, then for any n, there exists Z1 through Zn such that the set this is the class G. This class G projected onto Z1 through Zn is the full hypercube, 0, 1 to the n. It's a full hypercube. Now, if it's a full hypercube, what did we prove last time? Rademacher averages are 1. They don't go to 0. What this means is that if you take a class whose VC dimension, whose expressivity is infinite, you should not able to this line of analysis will just not work. Now, I still haven't talked about the learning problem, but let me now mention the learning problem. Is it possible to have this small when you have a VC infinite class and you know something very specific about the distribution, or your set of distributions is restricted? Yes. Can you have this small if you want the result to hold for all distributions? If the VC dimension is infinite, then you cannot say anything. So the VC dimension is only relevant if you want a distribution for your result, if you know nothing about the distribution. And that's somehow not a very interesting case anyway, right? You always know something about the distribution. And it could be that if you make even a few assumptions about the distribution, this whole thing just breaks down, right? So this is only relevant if you can't assume anything about the distribution. On the data. I was planning not to define it and just let you look at it. So, in fact, I already defined it here, kind of.
Is this a definition or just one-sided?
Yeah, it's a definition actually. So, VC dimension is infinite if for any n you can find points on which the projection is a full cube. And the VC dimension is d if for n larger than d you cannot find the points on which it's a cube. Okay, that's all. Should I write? Okay, maybe it's worth writing down. So VC dimension is d if for n larger than d. Okay, so this is up to 1, so I don't know if it's equal or greater or equal. I can never remember if it's a strict equality or not. There does not exist z1 through zn such that this projection z1 through zn is a hypercube. Is a binary class of binary functions, right? So this is a class of functions from some space x to 0, 1. You can make it -1, 1 also. Yes. Exactly. I'm going to write this in a second. Yep. Okay. Yes. Yes. Exactly. So that's the point about this is only relevant if you can't assume anything about the distribution, because the way that I would prove a lower bound, if you don't know anything about the distribution, I'll say the distribution is actually supported on those points, and then you can't do anything. Right? Because you will see those points roughly. Right? And so again, that's exactly the point. So VC dimension is irrelevant. Just because there exists some sequence, it doesn't mean that you cannot learn on average. Right? right? And especially if you assume something about the distribution, these sequences might be irrelevant. They will never occur in practice, right? Or under your assumption on the distribution, right? Good. So there is one kind of amazing thing about the VC theory, and that's why it became popular. If the VC dimension is D, it's finite, you could say, okay, well, I don't get the full hypercube after a certain point. When n is larger than a certain threshold, I don't get the full hypercube. So maybe I get a hypercube with one vertex removed, right? Or maybe two vertices removed. So the wonderful thing is it cannot happen. So either you get the full hypercube or you get a vanishingly small fraction of the hypercube. And that's kind of the famous Sauer-Shelah Wapner-Czerwonenkis theorem discovered in around 68, 69. So let me not write it down, but so if VC of G is finite, let's say is D, which is bounded, then for n larger than D, the cardinality is bounded by, I'm going to skip a lot of terms, but essentially it's something like n over e to the power d. Okay, so think of this as, I'm just going to write this slightly in a slightly looser version, roughly n to the power d. So it only grows polynomially in n. Right? This is an n-dimensional cube, so you would expect 2 to the n, maybe minus 1, 2 to the n minus 2. And this says, no, it cannot be. It has to be a really tiny, vanishing proportion. And that's why it became kind of an interesting and non-trivial result, because once you can establish, if you can establish this, and sometimes it's very easy to establish that the VC dimension is finite, then you know that after n surpasses this d, Rademacher averages will be bounded, right? Why? Because you take the log of this, and you get d log n. If the cardinality is less than n to the d, then log of the cardinality is bounded by d log n. So that's the result for VC classes. When we say VC classes, it just means it has a finite VC. Rademacher averages of the class G Zn are bounded by square root of, okay, there's some constant d log n over n, and with a bit more work you can actually remove this log d, so this doesn't have to be there. That's the result. Okay, this is only for binary classes. Yeah, so VC of G is equal to D, and that's finite. And we say non-VC if it's infinite. Okay. In particular, you can immediately read off this result. Take 2 points. Can you get the full cube as the projection of this class onto 2 points? All right, so you've got 2 points. You can get 0, 0, 1, 0, if the threshold is in between. And you can get 1, 1. Can you get 0, 1 with this class of functions? You cannot. So that's an immediate proof that the VC dimension is 1 for this class. So VC dimension of thresholds of this class G is 1 in this case. And therefore, we already have this result, and in fact, you should be able to remove log n. So it is 1 over square root of n convergence. Okay, so that's the story for for the VC theory. So a couple of remarks. Often, the VC dimension is the number of degrees of freedom, if you wish, roughly speaking, but that's not always the case. One example is if you take sine of x over alpha and vary alpha. You take the sine, so sorry, there are two signs. So you take the sine as a plus minus 1 of sinus, S-I-N-U-S, of x over alpha. That's a one parameter family, but has infinite VC dimension. So just don't fall into the trap thinking that VC dimension is always the number of parameters. Often it is, but not always the case. For hyperplanes in d dimensions, this was one-dimensional hyperplane, right? Think of this as a non-homogeneous hyperplane in one dimension. The analogous result for, so if you take sine of w times x, this is a function, and now you vary w in Rd. That's a class of binary valued functions. I guess in this case it's a plus minus 1, but doesn't matter. VC of this class is okay, it's either d or d plus 1, okay? So is it d plus 1? Maybe plus or minus 1. Okay, let me just all right. I mean, the main important thing is that it's order of d. Okay, so in this case, indeed, that's the number of degrees of freedom. Right? Somehow, you have a d parameter family, so that's the number of degrees of freedom. So. The
definition of VC dimension that I've seen before relates to the ability to be able to separate points.
Exactly.
It's slightly different definition.
It's exactly the same definition. What we're saying here is I give you data. What kind of sign patterns can you realize with your functions? Can you say that this is a cat, dog, dog, cat, cat, cat? If functions in your function class can assign arbitrary signs to this, or arbitrary zeros and ones, that exactly is the same statement that the projection is all of the hypercube. That's exactly the same statement. Make sense?
Yeah, I mean, I see the intuition.
Mm-hmm.
It's not entirely clear to me that they're mathematically equivalent.
They are, yeah. Yeah, this is equivalent to the usual VC dimension definition. In fact, many people state it this way. Again, there is this issue plus minus 1 that no one cares.
This is correct.
Okay. All right. So, what's next? Well, let's talk about a question. Yes.
So it feels like you're able to get a lot of these results, just like the symmetrization that like the bound and cardinality are like kind of magical. Like, how would you actually go about doing this?
Some of these things for other classes.
Or just like why is the symmetrization lemma true?
Why symmetrization lemma true? I could prove it. It would take me 10 minutes. Now the question is, do we want to do it, or should I just put it in the slides and maybe you look in the slide? Let me give a bit of intuition why this is the case. So here's the expected value of some random variable u, okay? I'm going to be very loose, kind of hand wavy, right? So this is the expected value. And now you draw random versions of this, right? They look like that, right? The center is that random variable, the mean, right? And now I want to look at u minus expected u. So I want to look at this distance. The problem is that I don't know what this expected u is. So instead what I could do is look at pairwise distances. And that will, up to a factor of 2, which is exactly that factor, gives me the right distance. That's the intuition. And I mean, the proof is not difficult. I just maybe do something slightly different instead. Okay?
Why are you looking at 2 minus?
Just intuition. The way it comes up is, yeah, I know. So, but the roles of that is this and that. So this is centered around that. Instead, what I'm going to produce, I'm going to produce another average. Now I have 2 averages, one minus another, and now I can instead look at sign flips, because these are just IID random variable. That's the idea. Maybe I will do it next class, the proof. Okay. Okay, so now
So everything we said now applies to the threshold, right?
that's correct.
And your
Well,
function has to be 0, 1, 2.
That's correct. That's correct. That's correct. Correct. Okay, so another thing that we kind of swept under the rug is that usually we have a loss function. And here we didn't even consider a loss function, right? That's a remark that was made. Right? So what if you have a class F, which is a class of functions from x to 0, 1. And then you create a class G, which is the loss class. That's the one we're interested in, right? Really. And this loss class, the loss function is indicator. So I want to take the indicator composed with f. So let me write it out. It's the x, y maps to whether the function f makes a mistake. In other words, whether y times f of x is less than 0, right? Correct?
You want to make it minus 1 plus 1?
Oh, yes. Thank you. Yes. Good point. Let's do minus 1 plus 1. Thanks. Yep. Another way to write it is y is not equal to f of x, right? That's just another way of writing it. So it turns out that Rademacher averages of G are one half times the Rademacher averages of F. So let me be a bit more specific. Rademacher averages, of G on x1, y1, xn, yn are equal to one half of the Rademacher averages of F projected onto x1, xn. Right? There is no y's. Okay? So you can erase, you can erase this loss function, and this is a one-line proof left for the homework. Okay. So everything we've done so far, indeed, you could have been talking about a prediction problem with thresholds, or a prediction problem with hyperplanes. This gives you a way to go from Rademacher averages of the loss class, which is this object, to the Rademacher averages for the function class itself. Okay? Make sense?
So what does it mean, the point of
Yes, that's right. And what I'm saying is you can forget about this L. For the problem of classification with indicator loss, you can just get rid of it. Okay, so that's that. And I'm not going to do any more homework for you. So you'll have to do it for, by yourself. And let me do a couple of minutes introduction into large margins and what we're going to do next. So imagine that I do this for hyperplanes. So I just told you that the VC dimension of hyperplanes is D. So if I go through this route, I end up here, and I get square root of square root of D over N. Right? So what you can say is, as long as the dimensionality is less than the number of data points, I'm going to be learning based on the data. So again, I observe data. I find a minimizer, the one that minimizes the empirical loss, separates the data the best it can with a hyperplane, in this case a homogeneous hyperplane, goes through the origin. And I have a guarantee that out of sample performance, relative to the best hyperplane I could ever find if I were God and I knew the distribution, is pretty close as long as n is larger than the ambient dimension, right? So kind of learning starts to kick in as soon as I see data points, more data points than dimensions for the hyperplane. Now, this does not assume anything about a margin or anything else, right? This is a purely result that relies on nothing, right? Just purely laws of large numbers. So this was realized by Vapnik and Chervenenkis already in around 65, 68. And after that, they built a more general Vapnik-Chervenenkis dimension and improved the Sauer-Shelah result. So, well, let's turn to neural networks. If we go with this idea that the VC dimension should be roughly the number of parameters, which is not true, right? But you can try to verify it. And indeed, there have been results in the 90s and more sharp results just a couple of years ago by, let's say, Peter Bartlett at Berkeley and others. Showing that the VC dimension of neural networks is roughly the number of parameters in the neural network with some other factors, right? So maybe more than the number of factors, but I think there is an additional factor of the depth maybe or something like that, okay? Now, that means that as soon as the number of parameters in the neural network is larger than the number of data, roughly speaking, you shouldn't be able to get anything from these results. Right? But the same is actually true for support vector machines, if you've seen those. They take your whatever your space, they lift it to so-called reproducing kernel Hilbert space. I guess we did have, Lorenzo talked about the reproducing kernel Hilbert spaces. Right? Now you're working with infinite dimensional functions. And the VC dimension, even though in that space things are linear, it's infinite dimensional. So the VC dimension of that class of functions is actually infinite. Right? And so the question is, why do those methods work well, even though the VC dimension is large? Right? So we have many examples, in fact, when VC dimension is a very crude notion of complexity, and it should not be taken as the right notion of complexity. It's just A, sufficient, but if it doesn't work, it doesn't mean that the problem is not doable. Right? It just has to be done in a different way. So this is one way of doing things. And we're not going to talk about neural networks in this lecture, but I want to get a results for hyperplanes at least that allows me to not depend on this dimension. If you remember, under the margin assumption in the first lecture that we did on statistical learning, we've got a out-of-sample performance guarantee in terms of the margin, and there was no dependence on the dimension. So why are we having a dependence on the dimension? Right? That motivates the large margin theory, and this was already understood in the 90s and led to so-called large margin classifiers theory. In other words, margin, the whole idea is that margin should replace the dimension somehow. If you've got margin, then you don't necessarily care about the dimensionality of the space. Right? That's an assumption about the problem about the distribution. It's an assumption on the distribution, and so it's clear that we're already going around the very conservative VC theory. Make sense? Okay, so let me use this display to roughly say what we're gonna do. We will keep this as the 0-1 loss. Actually, you know, we're going to start here. So we're not going to get a result of this form. We're going to get a result of that this is bounded by something. And I will mismatch. I will have a loss function here, which is different from the loss function here. Does that make sense? So here they match. Why do they match? Because we kind of started with the same loss here and here and introduced this three-term decomposition, two terms dropped, and then we were left with this. But I'm going to start with a different object.
So your ERM is using a different loss function than the intended one?
Actually, I'm not going to be using ERM. And we'll discuss the implication of the result a bit later. Yeah, so let's abandon ERM for now. Let's just fix a function f in the class f. Okay? And what I want to do is I want to consider expected 0-1 loss of there's one more thing that I'm missing in this picture. There's one more. Sorry, there's one more step that I need to make. My class F will be a class of real valued functions and then I will look at a class sine of f, which is just a set of functions x maps to sine of f of x. Okay? In other words, I'm generating a binary valued class from a real valued class by just looking at the sign of the prediction. Right? Now, arguably, this is what everyone does. When you work with a class of classifiers, you typically don't work with a class that maps x's to a classification immediately. You, in fact, have something that has a real value, like a neural network spits out a real value, and then you threshold it. right? If you ever implemented one of these, that's what you do in practice. So thresholding at 0, positive or negative, gives you the classification, the sign of the classifier. Right? So for the rest of the lecture, f is a class of real-valued functions, not binary. And from this, we can create a class of classifiers, which is just the signs of this f. Okay. We already did that here, right? That's one example of this. We took a class f of inner products, and then we looked at the sign, right? Hyperplane, just look at the sign, right? But this is a real valued. You can think of this as a real valued function. All right. So now that we've got this, I'm going to look at the 0-1 performance of sine of f so that's the indicator whether I made a mistake with my function f. Let me write this out. Yeah, so sometimes shorthands are could be confusing, I guess. So it's the expected indicator that sine of f is not equal to sine of f of x is not equal to y. Sorry. Right? And this is expectation over the xy pair. And now I need expectation. Let me write it this way. Okay? Let me do it this way. Now I can also write this as a expected indicator that y f of x is less than 0. That's another way of writing it, right? Expected over xy. Questions about this?
Don't we usually take the expectation of this over the sample?
We usually do, yeah, but this is still true. This is still correct. If you think of f as chosen with respect to the data, then this is a random variable in the data, and then you take expectation. Okay. So let me introduce a notion of surrogate loss functions. So consider the x-axis where we're going to plot y f of x. Okay, that we're going to plot this value. Yes. Just the xy. That's yeah, the p. So xy is from p. Right. So this is the a plot of this function, the indicator. The indicator says 1 if y f of x is less than 0, and then 0 otherwise, right? That's the plot of the how much we're going to pay if the sign is not correct. Now let me introduce the margin loss. The margin loss is going to be the same here, and then it will have a slope of 1 over gamma, come down to gamma, and then continue like that. So let me call this function phi or either phi or psi. I don't know which one I use. Let's see. Just to be consistent with the nodes, I use psi. So this is psi of y f of x. And so the definition of psi, okay, is of a is 0 if a is greater than gamma, 1 if a is less than 0, and then 1 minus a over gamma if a is between 0 and gamma. Right? Oh, wait. I use the, no, sorry. Yes. Sorry, so I'm going to use this C. Let me call it, just to be consistent with the notes. Sorry, a phi. Sorry, my Greek is not very good. So the phi function is going to be like that. So I'm going to introduce one more surrogate, which is the psi, and that's going to go like this. Okay, so psi of a is 1 if a is less than gamma, and 0 otherwise. Okay, everyone is clear on these functions? So the orange one is psi. All right. So what I know is is that the indicator of y f of x less than 0, which is my original loss function. That's the one I care about, really, right? Or at least I care about this function when it comes to out of sample performance. Right? I don't care about necessarily about other functions out of sample. This is upper bounded by the blue one, the phi of y f of x, and that's upper bounded by psi of y f of x. Okay, and that's true for every y f of x. Now I can define L phi to be, let's say L phi of f to be expected over xy pair phi of y f of x, and the same thing for psi and I can do the same thing for the empirical, right? This is the empirical version. Empirical f is 1 over n sum of phi of y I f of xi, and psi version of this is 1 over n sum of psi of y I f of xi. Okay, I haven't done anything. Right? I'm just defining a bunch of quantities.
Why isn't L phi and L psi defined the same way as L0 1?
It is, right? It is. So this is my definition, right? It's a function of y f of x, y times f of x. That's my 0, 1 loss. Maybe I've confused you by writing it this way, But I think this is consistent with what we've done before for the 0, 1 value functions. For 0, 1 value functions. Minus 1, 1 valid functions. Okay, so that's a bunch of definitions, and let's get to the punchline. So let me look at the expected max over f in f of L phi of f minus L hat phi of f. Okay? Why I'm doing it will be clear in a second. But let me just look at this. By the way, I'm not putting parentheses, but should be clear that this depends on f, so that's the max is over both terms, right? Okay, now because of this domination, because phi is lower bounded by the indicator, that's lower bounded by expected max of the L01 of, okay, now I have to write sign, right? Okay. Expected max L01. Can I just write L01 of f? It's clear that I take sign of the real valued f, right? Then it's closer to that definition. Minus L hat, so this is really sign of f. L hat of f. Oh no, sorry. So what am I going to put here? Here I'm going to actually go to the lower bound, right? Sorry, I'm going to the lower bound, so I want to subtract more. So I'm going to take an upper bound on phi, which is psi, like this. Correct? Because this is smaller than that, but what I'm subtracting is larger than that. So the inequality is correct. So in particular, for any f in f, it's L01 of f. What do I want to say? Let me cheat a little bit for a second. Okay. So let's not concentrate on the left side. This will hold with high. What do I want to say? Fine. Let's put expectation. Sorry. Let's put expectation. Okay, so now I've got uniform deviations, except my loss function is this ramp function. So the blue function is the ramp loss. Okay. There is no f hat. I just fixed any f, and for that f, this is upper bounded by the maximum. Here, f is just a dummy variable. Yeah, sorry. There's a hat. That's why. This is a random variable. Yeah.
The only difference between the first line and the second line is that
I dropped the max. I just dropped the max.
oh, the expectation is everything is inside the expectation.
Yeah,
Right?
yeah.
So,
Now, of course, this is just the L without the hat. But I do want it with a hat, and I will just. I'm hesitating between introducing high probability notions into this inequality. Let's forget about this side for now. I will come back to that. Let's develop the right-hand side. Okay. So the right-hand side gives me. Well, I can do symmetrization now. So I get a 2 expected Rademacher averages of phi composed with f projected onto the data, projected onto x1, y1, xn, yn. Now, if you remember contraction, it says that if I have a 1 Lipschitz function, I can remove it. Now, what if I have a L Lipschitz function? I didn't write it down, but if I have a L Lipschitz function, then I can remove that constant L and get L times the Rademacher averages of the original class. In this case, what is the Lipschitz constant of the blue function? How steep can it go? 1 over gamma. So I get 2 divided by gamma expected Rademacher averages of just my original class f projected onto x1 through xn. The y variables are gone. I'm cheating a little bit because in what I wrote last time, I used the same phi on every coordinate. Here I'm going to be using a different phi because there is a different y on each coordinate, but that turns out not to matter. So believe me that this result holds. Okay, and now that's all. That's the large margin result. Okay, so let me just write it I will discuss it in just a second. I'm going to write it with high probability, which essentially says, instead of this expectation, put probability on everything. Okay, so the result is like this. With probability at least 1 minus delta, so 95% probability, for any f in class F, L01 of f. Now I'm going to bring this object, this term, to the right-hand side, is upper bounded by L psi of f with a hat plus 2 over gamma times Rademacher complexity of f projected onto x1 through xn. Now I have to pay something for being delta certain, 1 minus delta certain. So what I pay is, you don't have to understand this, some constant log 1 over delta divided by n. This is the what's called the large margin bound, and I'll explain why. Large, or the margin bound. what is this object? Let's write it out. Let's write it out. What's another way to write the orange threshold? It's the, first of all, it's the empirical. We agree because I put a hat. So it's the empirical. Now, what are the losses on the points? The indicator that yi f of xi is less than gamma, which is exactly the proportion of margin mistakes that this function makes. If you've separated the data by a margin gamma, this term is 0. But in general, you could have some mistakes on the margin. So think of this being your data, let's say cats and dogs. This is your function that's separating the two classes. This is the margin. Now, there is a bit of a caveat. What is this space in which I'm drawing? I'm thinking of this as more like a geometric notion of being close to the boundary, right? If you worked on adversarial examples, you probably are more familiar with that notion. This being inside of this gamma region, the definition for me is that the f is not confident enough about predicting this y. In other words, f on that data point is less than gamma. It might be on the correct side, but it's not confident enough in its real valued prediction. Does that make sense? So again, f's are now real valued, but anything in this region is somehow f is not confident enough. Now, if you really want to think about this being geometry, then the Lipschitz properties of f come into play. Because if f is very steep, if f changes very quickly, then you might have points very close to the boundary on the different sides of in different classes. Right? The geometric distance between these cats could be small, but the function changes very rapidly, and that might be so some people studied this as a possible explanation of adversarial examples. Right? But in any case, this is the proportion of margin mistakes. Then you pay for complexity of the class f and 1 over gamma. That's what you pay. I did because I folded into this. It turns out that I can drop it and pay here. I'm sweeping a little bit under the rug because functions f need to be bounded for that statement. So if f is a class of bounded functions in absolute value, then I can fold it into this C. Okay. So example. Where was this? Class of, so f is a class of x maps to wx, where the norm of w, the L2 norm of w is equal to 1, or bounded by 1. So that's a class of hyperplanes in d dimensions. What are the Rademacher averages of the class f projected onto x1 through xn? I did not do that example, but it is bounded by, let's say, c, some constant over square root of n. I think it's just 1 over square root of n. Okay? If I have 1 minute, I will do that. For any x1, xn in also bounded norm. So if the norms of xi are bounded by 1. Let's compare this to perceptron. What does perceptron say? Perceptron had 0 here, and it had 1 over gamma squared times 1 over n. What did we get? So compare. We had 1 over gamma squared times 1 over n. Here we got one over gamma, I mean ignoring constants, times 1 over square root of n. This is square of that. Why did we pay this price? We paid this price because this worked in a hard margin condition when there can be no margin mistakes. Right? So here, this was the hard margin case. And here we've got this result with a soft margin. Whatever it is, let's call this the soft margin. There could be some mistakes on the margin. You pay for them. Hopefully not too much. But then you've got essentially a bit slower, but that's a generalization of the perceptron. Right? That's right. So the hard margin is that there exists a W star that separates, let's say, the distribution. So you'll never see data outside of the or inside of the gamma margin. For the linear case, the margin is the margin definition is exactly this notion, right? Y times W times X being less than gamma. That's right. So that's another interesting part. This holds for any f. The other result only holds for perceptron. So we've provided yet another generalization, right? You pick any function, this is a true relationship. So now you can say, why do we care? Well, what we do in the field is we optimize upper bounds, right? If we prove something with an upper bound, we try to optimize it. And that gives rise to an algorithm. So what should be the algorithm? The algorithm should be try to minimize the number of margin mistakes while keeping this small. What do I mean by that? Well, here we've assumed that the norm is 1. With a bit more work, you would be able to put a norm of W or a norm of F here, some norm of F. In other words, the game is keep the norm small while maximizing the margin. That's the algorithm that comes out of this. And that's support vector machines. And a lot of kind of motivation for large margin classification. Maximize the margin subject to keeping the norm small. Make sense? That is support vector machines. So more generally, I will continue next time, but more generally, when you get upper bounds of this form, it suggests an algorithm. This is an empirical objective, such as a margin. You can try to optimize it. And this is a penalty, a complexity. Now, it's a bit hard to see this as a complexity of the function that you're trying to choose, because that's a fixed class. But it's easy to convert this into complexity of your function f. In other words, the method is a regularization method. Margin plus some regularizer. In this case, it's the L2 regularizer. It is suggesting exactly the support vector machine style objective, which is maximize margin and penalize for the norm of the function. Okay. Now, I know that I went too fast. Maybe this should be 2 lectures next time. But hopefully you got a bit of a glimpse of how very simple set of inequalities. I mean, this is really the only set of inequalities that we've written. Right? It's really literally one line, plus we did contraction. We used this property, and we've got a margin-based result.
How do you get from here?
So the only thing I swept under the rug is a high probability statement, which requires you to know that these quantities are concentrated around their expectations. Okay, I'll see you next week.